Welcome. So in the last lecture, we are discussing about Minimax Search. So we'll continue our discussion on that. So basically, Minimax Search is used to find an optimal solution given an adversary is in the game who is trying to minimize our performance or who is counter attacking on us. Okay. So it is sure that Minimax Search will find an optimal solution in the presence of an adversary, assuming that the adversary is also giving his best. But there are some drawbacks with the Minimax algorithm. So first we'll be discussing that, and then we'll be discussing another algorithm which is called as alpha beta pruning, which is an improved version of the Minimax tree, Minimax search. So first let us try to understand what is the drawback with the Minimax algorithm. So let us consider a chess game, and let us try to understand how difficult it is to solve a chess game by using Minimax search. So it is observed that the branching factor of a typical chess game is it is close to 35. So you know what is branching factor? The number of child a node, the maximum number of child a node can have, it is close to 35. And the game length is, it is estimated to be approximately 100, which means player 1 makes 50 moves and player 2 makes 50 moves. In that case, the search space is this much, b to the power m, which is 35 to the power 100, which is close to 10 to the power 153, 154. This is a very huge state space. Now, if you see our universe, the universe contains this many atoms, 10 to the power 78 atoms. And this is the age of the universe as per the scientific estimation. This number is not a small number, it is a very big number. You can convert to years and check like how many years it is coming. It's so many years it is coming. Okay. And let us assume that there are this many moves in the universe at a given second, 10 to the power 8 moves in a given second, in 1 second. Then the universe can be represented with 10 to the power 8 into 10 to the power 78 into 10 to the power 18 states, which is 10 to the power 104, which is less than our number of states in the chess game. Right? Now, if you use Minimax search to solve the chess game, it has to explore all these states, which is practically infeasible. So it will not reach the solution at all, because it will keep on execute and it will keep on try to explore all the state spaces, and you will be running out of time. So achieving the exact solution or the optimal solution is completely infeasible with Minimax search. So now we are going to discuss another algorithm which is called as alpha beta algorithm, which is an improved version of the Minimax search. So basically, alpha beta procedure can speed up the depth first Minimax search. So Minimax search, it works in a depth first fashion. So here we use two parameters. One is called as alpha, the other one is called as beta. Alpha represents the lower bound of the max node. So in a Minimax algorithm, we know there are two nodes, max node and a min node. Max node will always tries to maximize his points, and the min node always tries to minimize the opponent's points. So alpha is a lower bound on the max node, and beta represents the upper bound on the min node. So what does it mean? So which means that we set a lower bound for alpha. We set a lower bound for alpha, and that lower bound is initially it is minus infinity. Initially, that lower bound is minus infinity. Now, what is the lower bound? Alpha will not accept anything less than this. Alpha will accept one thing, only values greater than this. Now, as the algorithm proceeds, say if the algorithm encounters a new value 10, now the alpha will accept this new value 10, because this 10 is greater than infinity. So minus infinity. So if you, because alpha is associated with max node always want to improve. So the new value of alpha will become 10. Okay. Say for example, now the new value is 10. Now as the algorithm proceeds, if it encounters a value 5, now alpha will not accept this value because this is a lower bound. It will not accept anything less than this. It will accept only things more than this. So now also alpha will remain as 10. Okay. So again, as the algorithm proceeds, alpha encounters another value 15. Now this 15 will be accepted because this is lower bound. It will accept something more than this. It will not accept anything less than this. So alpha now it will become 15, so on and so forth. So that is called as alpha, which represents the lower bound of the max node. So it accepts new value for alpha, that is it accepts new value v if v is greater than or equal to alpha. Okay. Then we have another parameter beta. Beta represents the upper bound on the minimizing node, and initially beta will be set as initially beta will be set as plus infinity. Okay, so it represents the upper bound on the min node. It's upper bound. Beta, if you recall, it always want to minimize. So it will accept lower value, but it will not accept higher values. So say as the algorithm proceeds, you are encountering a new value such a way that v is equal to say 15. Now will beta accept this? Yes, beta will accept this because this v is less than the current beta. So the new beta will be 15. Okay, fine. As long as it is less, it will accept. So now as the algorithm proceeds, it encounters a value 25. Beta represents upper bound. Will it accept 25? No, it will not accept anything more than 15 because current upper bound is 15. It tries to reduce this 15 even. It will not accept anything more than this. So beta will remain as 15, and that will be the upper bound. Say as the algorithm proceeds, it encounters some other value, say 5. Will beta accepts? Yes, beta will accept because this 5 is less than this 15. Okay. So now this is the upper bound. So like this, we use two parameters. One is alpha and the other one is beta. So what is the intuition behind alpha beta pruning? What is meant by pruning? Pruning means pruning means striking off certain nodes, striking off or removing certain nodes from the search. That is, we need not explore those nodes at all. That is what is called as pruning. So the whole logic is, let us explore this. Let us explore this tree in the similar to Minimax style, and let us try to understand the actual concept. So when this is explored as per Minimax style, what happens? Say here we have 0. So this is a depth first search, right? So go down, go down, go down, go down. So this is 84. Let us assume first we have explored only this 84, and this is a min node. So this 84 will come here. This 0 will be replaced with 84. Okay, and this is a max node. 84 and 0, this will be 84, but it will, of course, 84 and 0, this will be 84. Okay, but this is a min node, so 84 and 0, this will be 0, right? This is a max node. 0 and 0, this will be 0. Okay, now say that we have explored this minus 29 also. After exploring this minus 29, this will take minimum of this 2. So this will become minus 29. Now this is max of this. So minus 29 and 0, this will become 0. And this also remains as 0. This also remains as 0. Up to here it is fine. Now consider come to the other side. When you come to this side, and if you explore this minus 37, this minus 37, this is a min node, so this will take minus 37 at this point of time. Okay, this is max of this. Max of this is minus 29 minus 37. This will become minus 29. This is min of this 0 and minus 29. So this will become minus 29. This is max, so this will be 0. Fine, that is fine. Now the question is it required to explore this node or not? Actually, it is not required to explore this node. Why it is not required to explore this node? Because, say for example, this node takes a value minus 1000, very high number. If it is minus 1000, then what will happen to this node? This node also will take minus 1000 because this is a min node. Out of these two, minus 37 and minus 1000, it will take minus 1000. But what will be this max node's value? Out of this minus 29 and minus 1000, it will choose only minus 29. Right? This is one case. This is one extreme case. Let us assume this is plus 1000. If it is plus 1000, then this is a min node. If, let it be plus 1000 or plus 1 lakh or plus 10 lakh, whatever it may be. But this node will choose only minus 37 because it needs a minimum value. So it will choose minus 37. If it chose minus 37, then what this max node will choose? It will choose only minus 29. So irrespective of whether this is plus 1000 or minus 1000, this node's value is not going to change. It is going to remain as minus 29 only. So there is no point in exploring this node. So we can prune this node. We can prune this node. This is the whole intuition behind alpha beta pruning. Okay. Now similarly, if you walk through the tree, you will identify several places. You will identify several places at which you need not explore certain parts of the tree. So those parts can be pruned. So that is what is called as alpha beta pruning. Now this is the intuition. Now to implement this systematically, we use two variables. So whatever we have discussed, that is what is being explained here. So when we go like this, we can actually we came to know that this node we need not explore at all. So we can prune that node. Okay. So this is the intuition, but this can be systematically implemented by using a algorithm, and that algorithm is called as alpha beta pruning. So the actual working of the algorithm we'll discuss towards the end of the lecture. First we will discuss the concept. So here we maintain two variables. One is alpha and the other one is beta. Alpha represents the lower bound on the max node and beta represents the upper bound on the min node. Okay. And initially alpha will be set as minus infinity and beta will be set as plus infinity. So we are setting alpha as minus infinity and beta as infinity. So with this, let us continue. And when we can prune, so there we have discussed, we have identified one node that you can prune. So, but what is the condition? Is there any logic? Yes, there is a logic. If alpha is greater than or equal to beta at any point of time, if alpha is greater than or equal to beta, we will maintain alpha beta for every node. At any point of time, if alpha becomes greater than or equal to beta, then you can prune the entire subtree. Then prune the particular subtree, prune the subtree. So this is the logic. Let us see with this example. So here alpha minus infinity, beta is infinity. So pass down this value towards the tree. Okay, so it is a depth first kind of search. So this value is passed down to this node, again to this node, again to this node. Now check. Now check this node. Only we have explored this node. It is 84. So this is a min node. So this is a min node means this 0 will be replaced with 84. And this min value will, where it will come? It will come to beta. Min value is associated with beta. Max value is associated with alpha. Right? So this is a min node, so it comes to beta. But what is the condition when beta will accept? Beta will accept only values which are lower than its upper bound. Okay, currently what is the upper bound of beta? Currently the upper bound of beta is infinity. Currently beta is equal to infinity. So is it, so beta, this is upper bound. So it will not accept anything more than this. It will accept only things less than this. Is 84 is less than infinity? Yes. So it will accept. So it accepts beta equal to 84. This is just after exploring this node, right? This is only after exploring this node, but it has another node also. So explore this also. When you explore this, out of 84 and minus 29, which is smaller, minus 29 is smaller. So this node value becomes minus 29. And what about this beta? So beta currently the beta value is 84. That is the upper bound. So it will accept anything less than 84. So is minus 29 less than 84? Yes, minus 29 is less than 84. So new beta will become minus 29. New beta will become minus 29. Okay. So now this path is explored. Right. Now this is max node. This max node, it will take max of this. This node is minus 29. This is minus 29 and this is 0. So max of minus 29 and 0 is 0. So this is 0. Okay. So this reminds us 0. Fine. Okay. And so this 0 from, so this is max of minus 29 and 0. So this parent node, its value will be 0. Okay. See one thing, actually in these algorithms, you should not consider these zeros, right? These zeros you should assume it to be infinity. Okay, let us not consider these zeros. We don't know this. So in Minimax we assumed this 0, but here you have to initially you have to consider all these are what you call it is unknown. It is unknown. Okay, so at this point of time, what we know, only thing we know that along this path, when you follow this path, there is a solution which can be reached with a cost of minus 29. And here this is a min node and it will choose only the minimum cost. So there is a solution which can be reached at a cost of minus 29. Okay, and this value should be backed up now. This value should be backed up in the parent node. So in the parent node, it will be backed up where? This is a max node. So max node, where it will back up? Max node will back up this information. It will not back up in beta. It will back up only in alpha. Okay, so it will be backed up in alpha, like this minus 29. This alpha will be replaced with minus 29. Okay, this alpha will be replaced with minus 29. So this also, now our max node knows that there is a solution we can reach at most at the cost of minus 29, at least at the cost of minus 29. I can further improve this also, maybe if some other path comes, but so this means that max node knows that surely there is a solution with the cost of minus 29. There is so at least I can score this much points. That much the max node knows. Okay, fine. Now the max node, what it will do, it will pass on this information down the tree, like how originally the root node has passed this information down the tree. Now this node will pass the information down the tree to its unexplored nodes. Okay, so currently alpha is minus 29, beta is infinity. This information will be passed here. Alpha minus 29, beta is infinity. Okay, but at this point you check, is alpha greater than beta? No, alpha is less than beta, because beta is infinity, alpha is minus 29. Now say we are exploring this minus 37. When you explore this minus 37, this minus 37 will come here. And can we update beta? So beta will accept lower values. It will not accept higher values. So minus 37, is it lesser than infinity? Yes. So it will accept minus 37. Right? Now the new beta is minus 37. Now you check, is alpha greater than beta? Yes, minus 29 is greater than minus 37. So whenever alpha is greater than beta, we can prune that particular subtree. So prune this. We need not visit this. Okay, so that is the whole idea here. You can see here, this actually this zeros is misleading. So remove these zeros. There are no zeros. Okay, we don't know this. So we have only this. At this point, we have identified this is minus 29. So this value we want to back up. So when we want to back up, it is a max node. So it should be backed up to its alpha value. Okay. Now these values were passed down. And now we are exploring this minus 37. After exploring minus 37, what we came to know, alpha is greater than beta. So prune this, right? So that is how this node got pruned. Okay. Is that clear? So that is how this got pruned. Okay, fine. So like this we can prune many nodes when we use alpha beta pruning, and by doing that we can reduce the state space, we can reduce the size of the state space. So that is the whole logic. So let us continue, with our uh, process. Fine. Okay, so now what happens? Now if you see, this minus 29, this minus, here we have minus 29, we don't know this. Okay, we don't know this, so this we have to ignore. We don't know what is this value. So this minus 29 should be now backed up here. It should be backed up here. Now this is a min node. Okay, this is a min node. So minus 29 comes here, but it will come to which node? I mean which variable? It will come to beta. So alpha will remain minus infinity, but beta will become minus 29. Okay, so this beta will become minus 29, right? And this information will be now passed down. So here beta is minus 29, and this information you pass down to this node, pass down to this node, all the nodes. Now explore this node's child. It is 1. So this 1, will it replace this beta? Beta represents what? Beta represents the upper bound. That is, it will accept only values less than this. It won't accept anything greater than this. So already beta is minus 29. So it won't accept this one. Okay. So it won't accept this one. So now we have to explore this minus 43 also. When we explore minus 43, minus 43 is actually less than this, right? So minus 43, current beta is minus 29. So this will be accepted by beta. Don't consider this 0 at all. We are only comparing with beta. This one is not less than beta, current beta. So beta won't accept this. But whereas minus 43 is less than this. So now the new beta will become minus 43. So this will be minus 43. Okay. So this node value is minus 43. Okay. Alpha still remains as minus infinity. Now this information should be backed up. It will be backed up to a max node. So max node, what is this? Alpha. So this alpha, now this is a max node. So its alpha will take this minus 43. Okay. Whereas for this node, its beta is minus 43. Its beta is minus 43, right? But when you want to back up this value, okay, so what happens? This node's alpha will become minus 43. The parent nodes, yeah. So here you can see, now the parent, this value should be backed up to the parent, but the parent is a max node. So the parent's alpha will become minus 43. Okay. Now the parent will pass down these values to its child. So I mean this alpha and beta to its child. Okay. So this minus 43 minus 29 comes here. Now what is the child? First child minus 25, minus 75. Is minus 75 less than beta? Yes, minus 75 is less than beta. So it will accept. So it will become minus 75, right? Now after this becomes minus 75, you just check. See, originally this is minus 43 and minus 29. Okay, minus 43. So let us consider the previous step once. Minus 43 and minus 29. At that time, minus 43 is less than minus 29. Alpha is not greater than beta. But after exploring minus 75, now beta will becomes minus 75. Once beta becomes minus 75, now if you see, is alpha greater than beta? Yes, minus 43 is greater than minus 75. So that means we need not explore this subtree. So we can prune this. Okay, so that's the next step. So here we have pruned this. Okay. So this part we have pruned. This minus 49 we need not explore, right? So let us continue. Similarly, we should continue our process. Now So this please don't consider these zeros. Actually this is misleading. There is no such zeros in the alpha beta pruning. That zeros comes only in min max. Okay, so we don't know this, so we don't check this at all. Only we back up the uh, previous nodes, the child nodes value to the parent. Okay, to its corresponding either alpha or beta. Now this is minus 43. This should be backed up to the parent. Now parent is a max node. Parent is a max node. Okay, so where it will be, so this value where it will be backed up. So this node's value, we are backing up the value of the node. Okay, so this node value, where it will be backed up, it will go to alpha. So alpha becomes minus 43 and beta will be infinity, right? So alpha becomes minus 43. Yes, this is minus 43 and beta is infinity. Now as the next step, the algorithm, what it will do, it will pass down these values. It will pass down these values. So it will pass here also, this will become minus 43 and beta is infinity. Here also alpha becomes minus 43 and beta is infinity. Okay, this is infinity, right? Here also alpha is minus 43 and beta is infinity, right? No zeros here. Fine. Now you have explored this minus 21. This is minus 21. Currently, if you see, nowhere alpha is greater than beta. Alpha is less than beta in all places. Here, here. So here we explore minus 21, right? Is minus 21, is it less than the current beta? Yes. So this value becomes minus 21 and this also becomes minus 21. Okay, fine. Now you explore the other child also. When you explore the other child, this is minus 51. Okay, still alpha is less than beta, not greater than beta. So now this is minus 51 and minus 21, which is less than minus 51 is less than. And now can we replace the beta? Yes, because minus 51 is less than minus 21. So this becomes minus 51 and this also becomes minus 51. Now, okay, so this is minus 51. Alpha is minus 43, right? Now this value, okay, so uh, now now here we have minus 51. Now this node value is minus 51. This should be backed up. This should be backed up. So where it will be backed up? This is a max node, right? This is a max node. The previous node is a max node. Okay, just a minute. Yeah. So here currently our alpha is minus 43. We are at this level. Yeah. Alpha is minus 43 and beta is so here beta should also become, so we have taken this minus 51, right? So our beta should also become minus 51 here. Okay, fine. Now we are following this path. Now we are following this path. So when you follow this path, here already see, this is alpha is what? See alpha here why we are not updating the alpha? Here we got minus 51, right? This beta also it is minus 51, but why we are not updating the alpha? You may ask the reason. The reason is alpha represents what? Alpha will accept only, alpha represents the lower bound, right? It will not accept any value which is less than the current lower bound. It will accept value only which is greater than the current lower bound. But this minus 51 is less than minus 46, so it won't I mean this minus 51 is less than minus 43. Current value of alpha is minus 43. So it won't accept minus 51, right? So these same values will be passed down. Alpha minus 43, beta infinity, that is actually passed down. Okay. First it is, so initially it is passed down as alpha is minus 43 and beta is infinity. Once you explore 58, when you explore 58, beta will become 58. This node also becomes 58. But after you identify minus 46, this becomes minus 46 and this node also will become minus 46. Is that clear? Okay. Now what is this value minus 46? And this is a max node. It will take the maximum of this. So what's the maximum of this? Minus 51 minus 46, it is minus 46. Okay. Now only it gets minus 46. In the previous round, it is not minus 46. In the previous round, it is minus 51 only. Okay, here it will be originally minus 51, but alpha won't change. After identifying this, this becomes minus 46, right? Okay, fine. But now also our alpha will not change. Why alpha is not changing? Alpha is not changing because minus 46 is not greater than minus 43. Minus 46 is less than minus 43. Alpha will accept only better values. Is that clear? Okay, fine. Now this is minus 43. This is minus 43. This we don't know. Okay, this is minus 43. So if you go back to here, yes. Originally beta is infinity. Originally, previously beta is infinity. At this point, actually beta is infinity. But alpha, but this is a min node. This is a minimum node. So it will accept values which are less than infinity, right? It will accept values which are less than infinity. So this is what? Minus 46. Is minus 46 less than infinity? Yes. So it will accept. So this new beta value becomes minus 46. So the updated beta value becomes minus 46. And now if you see, is minus 43 greater than minus 46? Yes. Minus 43 is greater than minus 46, which means we can prune this entire subtree. We need not search this. These entire things can be pruned up, right? So this is the whole idea behind alpha beta pruning. That is, with alpha beta pruning, we are reducing the number of nodes that is to be what you call, that is to be searched in a minimax tree. And here is the algorithm. So this is for min node, this min val, and this is for max node, which is represented as max val. So let us see the max val part first. So it takes a state. State means a node, and its alpha value and beta value, and it checks whether it is a terminal state. Terminal state means it's a leaf node. If it is a leaf node, return the utility value of that state. Okay. Otherwise, for every children you do this. For s in children of state, right? For let us assume the tree is like this. Okay, this is the tree. Let us assume the tree is like this. Okay. Let us assume these are the leaf nodes. Okay, now let us assume this state we are talking about. Yes. So is it a terminal state? No, it's not a terminal state. Then for s in children of state, yes in children of state, you are calling what? Child equal to min val s comma alpha comma beta. So every node has alpha beta, right? So now for this node's child, you are passing this node's first child to min val. This is max val. Similarly, we have min val. Min val is this function, right? For this function, it is passed. Again, this function checks whether it is whether that child node is a terminal node or not. Okay, it's not a terminal node. Then again, for every children of that node, it is going to call the max by passing s, alpha, and beta. Right. Then for this node's child, max is called. Then it checks, that is this node. It checks whether this is a terminal node. No. Then for every node of this child, it is going to again call min node, right? Min val. So now this node is passed for min val. It checks whether it is a terminal state. Yes. Then return the utility. Okay, what is its utility? Utility is whatever the value here. Say the value is 5, that will be returned. Where it returns? It will return to Who called this function? Maxwell. So it will return to here. So this particular child, it will get the value as what? 5. Okay, for one node. Then what we get, what we calculate, alpha equal to max of alpha comma child. Already it has some alpha value. Initially its alpha value will be minus infinity comma 5. So it will take 5. So alpha is updated to 5. Initially alpha will be minus infinity, right? If alpha is greater than beta, so beta is infinity. So alpha is not greater than beta. If alpha is greater than beta, it would return child. But now alpha is not greater than beta. Like that, the loop continues. Okay, like that the loop continues. Otherwise, now it is not greater than beta. So now it does for the next child. Now for the next child, it calls min value. Then it gets that node. Are you getting? So min val means this will be called. Again, is it a terminal node? Yes. So return the utility. So the utility will come here. Now the utility, say it is 7. Okay. Previous alpha value is 5. So alpha is equal to max comma alpha comma child. So now alpha will become 7. Is alpha is greater than beta? No. So again look for another child. There is no other child. There are 2 childs. So it returns. Okay. So it returns, then it returns, then it will come here. It will return, and here what it will return? It will return that 7 it will return, right? It will return 7, and further it will call beta equal to min of beta comma child. Okay, so so here I am assuming this as max node. So 5 and 7 means here it got 7. Okay, so now this 7 is passed here. Child is having 7. Child is having 7, and beta, originally beta is infinity. So it takes min of infinity comma 7. What is that? 7. So now beta will be updated to 7. Okay, now beta will be, new value of beta will be 7. Is alpha greater than beta? What is alpha? Our alpha is also 7 at this point of time. Okay, as alpha is greater than or equal to beta, then it will return that child. So whenever alpha greater than beta, it returns the child, which means that part of the tree can be pruned off. Okay, so that is how. So whatever we have discussed, no, the same thing here, it is represented as algorithm. So the beauty of the algorithm, you can see, it is the max is calling min and min is calling max. It does repetitively, and it checks if alpha greater than or equal to beta, it returns the child. Say if alpha is not greater than beta, then it creates all the child. If alpha is not greater than beta, yeah, uh, fine. See, actually here you should check one thing. It's not, it won't compare with 7. It will compare with the original value of alpha. It's a recursion kind of thing. Originally it is alpha is minus infinity. So beta is 7. So it won't return. So minus infinity is not greater than 7, right? So it will identify all the child now at this level. Okay. At the next level, it will identify all the child, and so on and so forth. It continues. So basically, it checks this min node. It generates all the nodes, and it identifies the one with the minimum node. Meanwhile, if alpha becomes greater than beta, it returns that particular node and it prunes that particular subtree. Otherwise, it generates all the node and returns the minimum of all the nodes. And the max algorithm, it does the reverse. Okay, it also generates all the node. While generating at any point, if alpha becomes greater than beta, then it returns that child and prunes the remaining subtree. Otherwise, it identifies the max of all the child and returns that. Okay, so let us stop here. Fine, thank you.